Good afternoon. First, I want to acknowledge my co-author, Wang, for his essential contribution to this study. So from continuous GPS position time series, we can actually estimate the site velocity and together with this uncertainty. And it's this kind of estimated site velocity and uncertainty has a lot of geophysical and geodetic applications, such as the reference frame realization. And it's not uncommon to find out this kind of offset in the continuous time series. So we call it data break. And this data break can be due to either natural or artificial factors, such as the earthquake, the equipment change, or the change in the processing strategy. And as the length of the time series get longer and longer, and as we improve the data break detection algorithm, so this the total number of this data break could be increased. So our study focused on how this increased number of data break going to impact the uncertainty in the set velocity, and how it's going to impact the stability of the reference frame. If we have a continuous time series and we have a couple data breaks, we can still estimate the velocity for this site. So we can use this observation equation, where yt is the position of these sites observed at the FST, c is a constant term, and r is the velocity of these sites. And we also include these annual terms. And we will, because we have these data breaks in time series, we will need to use these heavy size stem functions to describe the behavior of this, the effect of this data break. So this ET here denotes the observational error. So if we put all these parameters we need to estimate in the unknown vector, so it includes this c, the velocity, the annual amplitude, and the magnitude of the data break. Then if we are given this covariance matrix for the observation noise, then we can just apply the sphere principle to estimate the velocity. And also we can extract the velocity uncertainty from this posterior covariance matrix, which depends on the observation noise covariance matrix. Now, in order to realistically estimate the uncertainty in the site velocity, we need to know what is the realistic covariance matrix for the observation noise in the GPS time series. And Williams et al. In 2004, they did a very comprehensive of the GPS time series from about 1,000 globally distributed GPS sites, and they just calculated the average power spectrum for the noise, and this figure shows the average power spectrum in the three directions. So what we can see from this figure is that as the high frequency and this spectrum flatten out, that means that there could be some white noise existed at high frequency. But at the middle frequency and the low frequency band, it's the behavior of the spectrum follows the power law. That means the power of at the frequency edge is a function of the frequency to the power of kappa. So these are called the power law noise. This is a very typical noise in the geophysical signal. And we can see here when kappa take different value, this represents different noise types. When kappa is equal to 0, that is white noise. When kappa is equal to -1, that's frequent noise. Kappa equal to -2, that's a random mode. And Williams et al. In 2040 also estimated these kappa values for this 1,000 continuous GPS time series. So they actually generated this histogram for the estimated kappa value. What we can see here is like the kappa value, this histogram is centered around -1. That means most of the GPS time series has a flicker noise. But this histogram always spreads out on both sides of the -1. That means the actual noise type in the GPS time series is very diverse. Therefore, we check a wide range of different error models. So it includes the power law noise with different kappa values. We also check the first order Gauss micro model with different correlation length. We also check the flicker noise, because previous study gave several different forms of the covariance matrix for flicker noise. So here we choose to compare among these different forms of covariance matrix to see whether it's gonna significantly impact our result. We also include random walk and white noise. And here we also include a mixture model which consists of flicker noise plus white noise with different magnitude variations. And as we previously mentioned, the velocity uncertainty actually depends on the covariance matrix of the observational noise. Therefore, we wanted to first to construct the covariance matrix for each of these included noise models. Unlike the first order Gauss micro model and the white noise model, obviously these two models has the analytical expression for the covariance. For most of the power laws, there's no such analytical expression exists for the covariance matrix. Therefore, we use this numerical method to construct the covariance matrix for these models, for the power law models. So what we did is like when we have a power law for a specific kappa value, we can apply the inverse Fourier transform to get the covariance matrix, the covariance function. When we have the autocorrelation function, then we can construct the initial covariance matrix based on this autocorrelation function. And based on this initial covariance matrix, we can synthesize a 400-decade-long noise time series with a daily sampling rate. In order to make sure this simulated noise time series has the same statistical character, we choose to scale this initial covariance matrix so that all the mean RMS of the simulated noise is equal to 1 millimeter. So in this case, we can make sure all these time series will have the same fluctuation energy. So this figure here shows the sample we generated for each of the model. Here we only show one sample. We can see for the white noise it's pretty random. For the random walk, we can see very obvious temporal correlation, but they all have the same fluctuation. When we have the covariance matrix for each of the model, then we can start to estimate the rate velocity by using the covariance matrix, and also by assuming different number of data breaks within the 10-year-long time series. So we gradually increase the number of data breaks from 0 to 21 and estimate the corresponding velocity uncertainty associated with each given number of data breaks. So from this figure, we can see for all these temporary correlated noise, they always produce greater rate uncertainty than the white noise does if there is no break at all. But when there is a data break started to add it into the time series, we can see whatever the noise model is, the uncertainty in the rate will increase with the addition of the data break. So for a better description of the sensitivity of the rate uncertainty to the data break, we calculate this growth factor, which is calculated as the ratio between the uncertainty associated with a given number of data break to the uncertainty if there is no break at all. So this number actually reflects the number of times the uncertainty will be increased by a given number of data break. So we can see here, it's very interesting to see it's like this growth factor actually is all linearly dependent on the number of data breaks. It doesn't matter it's a temporary correlated or it's a white noise, but they will have the inflation of this uncertainty in the rate. Actually, they have different inflation rate. For the random walk, for the white noise, it's independent. There is no correlation at all. Therefore, it shows the biggest inflation rate. But when the degree of temporal correlation gets bigger and bigger, then this inflation rate gets slower and slower. For the random walk, which is at the very bottom, I'm sorry, you can probably not see it. It's actually very bottom is flat. Because the random walk has the strongest temporal correlation, therefore the inflation due to the data break can be barely seen in this figure. Therefore, because it's all linear relationship, so we decided to fit inflation rate from this for each of the model, and then use this fitted rate to measure the sensitivity of the rate uncertainty to the data breaks for each of these models. And because from this figure we can show obvious dependence of the sensitivity on the degree of correlations. Therefore, this kind of very obvious relationship motivates us to try to see if we can find out an analytical expression to describe this kind of dependence. Because we have already defined a measure for the sensitivity. We still need to define a measure for the correlation, for the degree of correlation of the model. What we did is like we can use this covariance function, and then for each of the simulated noise time series, we can estimate a covariance maximum function, and then we average all these 400 covariance functions. So in this figure, it shows the average covariance function estimated for each of the noise model. Then we define this, we find out a time lag at which the covariance value decreases from 1 to 1 over E. Then this time lag is defined as the correlation length, and we use this correlation length to measure the degree of correlation in this measure model. Then we can plot this estimated correlation length against the sensitivity for each of the models. So from this figure, we can definitely see this blue, this green, right? This green dot is indicates this white noise. It has the greatest sensitivity, but when there is a very weak correlation exists in the noise, then this kind of sensitivity decreases dramatically. That means, for example, so here from the correlation length increase from 0 to a couple of days, then this kind of sensitivity very rapidly decrease. And as the correlation length gets even longer, then this kind of decrease gets slower, but it still follows exponential decay. Therefore, we choose to use a double phase exponential function to fit this data, and this double phase exponential function is showed as this red dashed line. So it has two terms. The first two terms account for the very rapid decrease in the sensitivity at the very beginning, and the second term accounts for the slower exponential decay. For conclusion, the estimated rate velocity becomes more uncertain as the number of data breaks increase. So no problem for this one. But how fast the uncertainty increase really depends on the degree of the temporal correlation of the observation noise. And if we just assume the observation noise is white noise, then we will seriously overestimate the sensitivity of the rate uncertainty to the data breaks. But for the current GPS time series, the most likely model is a mixture of flicker noise plus white noise. And for this model, if we increase the number of data breaks from 1 to 2 per 10 years, then this uncertainty in the rate will be inflated by only 11%. That is really not very significant. And therefore, the existence of the data break is not a major factor undermining the stability of the reference frame. Once the temporal correlation of the error is properly accounted for. And the practical implication for this study is for the equipment replacement. Because the equipment replacement is very important to improve the GNSS data quality. And in practice, we always measure the offsets before and after the equipment has been replaced. Therefore, this kind of thing further lessens the impact of the data break. Therefore, people should feel free to replace the equipment whenever it is necessary to improve the data quality. Thank you.
Unfortunately, we've run out of time at the moment, and that concludes our analysis and reference track session. Could I thank all of the presenters for their presentations? Thank you.
Okay, it's really amazing, the session 1. So now it's time for us to have the coffee break. But there will be something interesting happening here during the break, 20 minutes. So one of our sponsors, the High Target Company, we're going to introduce something they made in the past years for the real-time precise positioning services. You will be really appreciated if you just go outside and grab a coffee and then come back. But it's not required. You can just do whatever thing you want.